Hello there. So we are going to do the reading of the energy homework packet. Starting here with what is energy. So like always, let's take a look at the reading preview, the key concepts, the key terms. Key concepts are how are energy, work, and power related? And then what are the two basic kinds of energy? Some key terms here like energy, kinetic energy, potential energy, gravitational potential energy, and elastic potential energy, all things to look for. All right, let's get started. Brilliant streaks of lightning flash across the night sky. The wind howls and thunder cracks and rumbles. Then a sound like a runaway locomotive approaches, growing louder each second. Whirling winds rush through the town. Roofs are lifted off buildings. Cars are thrown about like toys. Then, in minutes, the tornado is gone. The next morning, a light breeze carries leaves past the debris. The wind that destroyed buildings hours before is now barely strong enough to move a leaf. Wind is just moving air, but it has energy. When a breeze does work lifting leaves, it transfers energy to them. Energy, work, and power. When wind moves a house or even a leaf, it causes a change. In this case, the change is in the position of the object. Recall that work is done when a force moves an object through a distance. The ability to do work or cause change is called energy. So the wind has energy. Work and energy. When an object or living thing does work on another object, some of its energy is transferred to that object. You can think of work, then, as a transfer of energy. When energy is transferred, the object upon which the work is done gains energy. Energy is measured in joules, the same units as work. Power and energy. You may recall that power is the rate at which work is done. If the transfer of energy is work, then power is the rate at which energy is transferred, or the amount of energy transferred in a unit of time. So power is how much energy is transferred in a certain amount of time. Power is involved whenever energy is being transferred. For example, a calm breeze's power is its rate of energy transfer to lift a leaf a certain distance. So how much power does the wind have? The tornado in Figure 1 transfers the same amount of energy when it lifts the leaf the same distance. However, the tornado has a greater power than the breeze because it transfers energy to the leaf in less time. Kinetic energy. Two basic kinds of energy are kinetic energy and potential energy. Whether energy is kinetic or potential depends on whether an object is moving or not. A moving object, such as the wind, can do work when it strikes another object and moves it some distance. Because the moving object does work, it has energy. The energy an object has due to its motion is called kinetic energy. The word kinetic comes from the Greek word kinetos, which means moving. Factors affecting kinetic energy. The kinetic energy of an object depends on both its mass and its velocity. Kinetic energy increases as mass increases. For example, think about rolling a bowling ball and a golf ball down a bowling lane at the same velocity. The bowling ball has more mass than the golf ball. If both balls have the same velocity, the bowling ball is more likely to knock down the pins because it has more kinetic energy than the golf ball. Kinetic energy also increases when velocity increases. For example, suppose you have two identical bowling balls and you roll one so it moves at a greater velocity than the other. You must throw the ball harder to give it the greater velocity. In other words, you transfer more energy to it. Therefore, the faster ball has more kinetic energy. There is a mathematical relationship between kinetic energy, mass, and velocity. 0.5 times mass times velocity squared. Do changes in velocity and mass have the same effect on kinetic energy? No. Changing the velocity of an object will have a greater effect on its kinetic energy than changing its mass by the same factor. This is because velocity is squared in the kinetic energy equation. For instance, doubling the mass of an object will double its kinetic energy, but doubling its velocity will quadruple its kinetic energy. Let's take a look at Figure 2. Kinetic energy increases as mass and velocity increase, right? Makes sense. If this goes up, kinetic energy increases. If this goes up, kinetic energy increases. So looking here, equal velocities, equal speeds, because the bowling ball has a greater mass, it has greater kinetic energy compared to the golf ball, less mass. If they are the same mass, they're both the same size bowling ball, the one with less speed, less velocity, will have less kinetic energy. All right, potential energy. An object does not have to be moving to have energy. Some objects have stored energy as a result of their positions or shapes. When you lift a book up to your desk from the floor or compress a spring to wind a toy, you transfer energy to it. The energy you transfer is stored or held in readiness. It might be used later when the book falls to the floor or the spring unwinds. Stored energy that results from the position or shape of an object is called potential energy. This type of energy has the potential to do work. So this skier up here has more gravitational potential energy because it is higher up. Also, the weight of an object gives it more potential energy. So this skier has more gravitational potential energy because he weighs more. Gravitational potential energy. Potential energy related to an object's height is called gravitational potential energy. Gravitational potential energy of an object is equal to the work done to lift it. Remember that work equals force times distance. The force you use to lift the object is equal to its weight. The distance you move the object is its height. You can calculate an object's gravitational potential energy using this formula: weight times height. For example, the red skier on the left, this is what we just looked at, weighs 500 newtons. If the ski jump is 40 meters high, then the skier has 500 newtons times 40 meters, or 20,000 joules of gravitational potential energy. The more an object weighs, or the greater the object's height, the greater its gravitational potential energy. At the same height, a 600 newton skier has more gravitational potential energy than a 500 newton skier. Similarly, a 500 newton skier has more gravitational potential energy on a high ski jump than on a low one. All right, elastic potential energy. The further the string is pulled, the greater the bow's elastic potential energy is. Pulling the string changes the bow's shape and stores elastic potential energy. So, elastic potential energy. An object gains a different type of potential energy when it is stretched. The potential energy associated with objects that can be stretched or compressed is called elastic potential energy. For example, when an archer pulls back an arrow, the bow changes shape. The bow now has potential energy. When the archer releases the string, the stored energy sends the arrow flying to its target. All right, next section, energy transformations and conservation. Key concepts. How are different forms of energy related? What is a common energy transformation? And what is the law of conservation of energy? So, of course, key terms: law of conservation of energy, energy transformation, and matter. The spray bounces off your raincoat as you look up at the millions of liters of water plunging towards you. The roar of the water is deafening. Are you doomed? Fortunately not. You are on a sightseeing boat at the foot of the mighty Niagara Falls. The waterfall carries the huge amount of water that drains from the upper Great Lakes. It lies on the border between Canada and the United States. What many visitors don't know, however, is that Niagara Falls serves as much more than just a spectacular view. The Niagara Falls area is the center of a network of electrical power lines. Water that is diverted above the falls is used to generate electricity for much of the surrounding region. Energy transformations. What does flowing water have to do with electricity? You may already know that the mechanical energy of moving water can be transformed into electrical energy. Most forms of energy can be transformed into other forms. A change from one form of energy to another is called an energy transformation. Some energy changes involve single transformations, while others involve many transformations. So let's take a look at these examples here. A toaster transforms electrical energy into thermal energy. Your body transforms the chemical energy in food into mechanical energy for you to use when you play sports. A cell phone transforms electrical energy to electromagnetic energy. Single transformations. Sometimes one form of energy needs to be transformed into another to get work done. You are already familiar with many such energy transformations. For example, a toaster transforms electrical energy to thermal energy to toast your bread. A cell phone transforms electrical energy to electromagnetic energy that travels to other phones. Your body transforms the chemical energy in your food to mechanical energy that you need to move your muscles. Chemical energy in food is also transformed to the thermal energy your body uses to maintain its temperature. Multiple transformations. Often, a series of energy transformations is needed to do work. For example, the mechanical energy used to strike a match is transformed first to thermal energy. The thermal energy causes the particles in the match to release stored chemical energy, which is transformed to thermal energy, and the electromagnetic energy you see as light. In a car engine, another series of energy conversions occurs. Electrical energy produces a spark. The thermal energy of the spark releases chemical energy in the fuel. The fuel's chemical energy, in turn, becomes thermal energy. Thermal energy is converted to mechanical energy used to move the car, and to electrical energy to power more sparks. Transformations between potential and kinetic energy. One of the most common energy transformations is the transformation between potential energy and kinetic energy. In waterfalls such as Niagara Falls, potential energy is transformed to kinetic energy. The water at the top of the falls has gravitational potential energy. As the water plunges, its velocity increases. Its potential energy becomes kinetic energy. Energy transformation in juggling. Any object that rises or falls experiences a change in its kinetic and gravitational potential energy. Look at the orange in figure 11. That's what the guy's holding, apparently. When it moves, the orange has kinetic energy. As it rises, it slows down. Its potential energy increases as its kinetic energy decreases. At the highest point in its path, it stops moving. Since there is no motion, the orange no longer has kinetic energy, but it does have potential energy. As the orange falls, the energy transformation is reversed. Kinetic energy increases while potential energy decreases. Energy transformation in a pendulum. In a pendulum, a continuous transformation between kinetic and potential energy takes place. This is a pendulum. At the highest point in the swing, the pendulum in figure 12 has no movement, so it only has gravitational potential energy. So at the ends here, almost like when you're on a swing, when you feel that pause moment before you swing back down. As it swings downward, it speeds up. Its potential energy is transformed to kinetic energy. The pendulum is at its greatest speed at the bottom of the swing. There, all its energy is kinetic energy. And then as it starts to move up, it gains potential energy again. Pole vaulter, similar experience. Lots of potential energy right here. Kinetic energy as it falls down. As the pendulum swings to the other side, its height increases. The pendulum regains gravitational potential energy and loses kinetic energy. At the top of its swing, it comes to a stop again, and so the pattern of energy transformation continues. Energy transformation in a pole vault. A pole vaulter transforms kinetic energy to elastic potential energy, which then becomes gravitational potential energy. The pole vaulter you see in figure 13 has kinetic energy as he runs forward. Okay, so kinetic energy running forward. There's some kinetic energy because they're always moving, but they've got elastic energy as this bends back. Let's keep reading. The pole vaulter you see in figure 13 has kinetic energy as he runs forward. When the pole vaulter plants the pole to jump, his velocity decreases and the pole bends. His kinetic energy is transformed to elastic potential energy in the pole. As the pole straightens out, the pole vaulter is lifted high into the air. The elastic potential energy of the pole is transformed to gravitational potential energy of the pole vaulter. Once he is over the bar, the pole vaulter's gravitational potential energy is transformed back into kinetic energy as he falls toward the safety cushion. Conservation of energy. If you set a spinning top in motion, will the top remain in motion forever? No, it will not. Then what happens to its energy? Is the energy destroyed? Again, the answer is no. The law of conservation of energy states that when one form of energy is transformed to another, no energy is destroyed in the process. According to the law of conservation of energy, energy cannot be created or destroyed. So the total amount of energy is the same before and after any transformation. If you add up all the new forms of energy after a transformation, all of the original energy will be accounted for. Energy and friction. So what happens to the energy of the top? As the top spins, it encounters friction with the floor and friction from the air. Whenever a moving object experiences friction, some of its kinetic energy is transformed into thermal energy. So, the mechanical energy of the spinning top is transformed into thermal energy. The top slows and eventually falls on its side, but its energy is not destroyed, it is transformed. The fact that friction transforms mechanical energy to thermal energy should not surprise you. After all, you take advantage of such thermal energy when you rub your cold hands together to warm them up. The fact that friction transforms mechanical energy to thermal energy explains why no machine is 100% efficient. You may recall that the output work of any real machine is always less than the input work. This reduced efficiency occurs because some mechanical energy is always transformed into thermal energy due to friction. Good old Einstein. Energy and matter. You might have heard of Albert Einstein's theory of relativity. His theory stated that energy can sometimes be created by destroying matter. Matter is anything that has mass and takes up space. All objects are made up of matter. Just as one form of energy can be transformed to other forms, Einstein discovered that matter can be transformed to energy. In fact, destroying just a small amount of matter releases a huge amount of energy. Einstein's discovery meant that the law of conservation of energy had to be adjusted. In some situations, energy alone is not conserved. However, since matter can be transformed to energy, scientists say matter and energy together are always conserved. Last section, energy and fossil fuels. Take a look at the key concepts. What is the source of the energy stored in fossil fuels? How is energy transformed when fossil fuels are used? Key terms, fossil fuel and combustion. Imagine a lush green swampy forest. Ferns as tall as trees block the view. Enormous dragonflies buzz through the warm, moist air. Huge cockroaches, some longer than your finger, crawl across the ground. Where is this place? Actually, a better question to ask would be, when is it? The time is more than 400 million years ago. That's even before the dinosaurs lived. But what does this ancient forest have to do with you? Formation of fossil fuels. The plants of vast forests that once covered Earth provide the energy stored in fuels. A fuel is a material that contains stored potential energy. The gasoline used in vehicles and the propane used in a gas grill are examples of fuels. Some of the fuels used today were made from materials that formed hundreds of millions of years ago. These fuels, which include coal, petroleum, and natural gas, are known as fossil fuels. The vast ancient forests were the source of coal. When plants and animals died, their remains piled up in thick layers in swamps and marshes. Clay and sand sediments covered their remains. The resulting pressure and high temperature turned the remains into coal. Energy from the sun. Remember that energy is conserved. That means that fuels do not create energy. So if fossil fuels store energy, they must have gotten energy from somewhere else. But where did it come from? Fossil fuels contain energy that came from the sun. In fact, the sun is the source of energy for most of Earth's processes. Within the dense core of the sun, during the process of nuclear fusion, nuclear energy is transformed to electromagnetic energy as well as other forms. Some of this electromagnetic energy reaches Earth in the form of light. Let's take a look at figure 18. The sun transforms nuclear energy to electromagnetic energy. Ancient plants and animals transform electromagnetic energy from the sun to stored chemical energy. Their remains become coal. Coal is burned to make steam, transforming stored chemical energy to thermal energy. The sun's energy on Earth. When the sun's energy reaches Earth, certain living things, like plants, algae, and certain bacteria, transform some of it to chemical energy. Some of the energy in the chemical compounds they make is used for their daily energy needs. The rest is stored. Animals that eat plants store some of the plant's chemical energy in their own cells. When ancient animals and plants died, the chemical energy they had stored was trapped within them. This trapped energy is the chemical energy found in coal. Use of fossil fuels. Fossil fuels can be burned to release the chemical energy stored millions of years ago. The process of burning fuels is known as combustion. During combustion, the fuel's chemical energy is transformed to thermal energy. This thermal energy can be used to heat water until the water boils and produces steam. In modern coal-fired power plants, the steam is raised to a very high temperature in a boiler. When it leaves the boiler, it has enough pressure to turn a turbine. So remember up here, it said coal is burned to make steam, transforming stored chemical energy to thermal energy. The graphic continues down here, okay? The steam turns turbines, transforming thermal energy to mechanical energy. The turbines spin electric generators, transforming mechanical energy to electrical energy. And then your hairdryer transforms electrical energy to thermal energy. A turbine is like a fan, with blades attached to an axle. The pressure of the steam on the blades causes the turbine to spin very fast. In this process, the thermal energy of the steam is transformed to the mechanical energy of the moving turbine. The turbines are connected to generators. When turbines spin them, generators produce electricity. As you can see in Figure 18, a power plant transforms chemical energy to thermal energy to mechanical energy to electrical energy. This electrical energy is then used to light your home and run other devices, such as a hairdryer. All right, I hope this was helpful.